Greetings dear friends, welcome back to my channel. It's actually been very long. I've not posted any other video, but right now we are going to jump into the world of switch mode power supply. As you can see here is a sample circuit in which you get to practice and know how to design such. Here is a switch mode power supply for converting from AC 220 and providing an output of 24 volt using the half bridge topology methodology actually. So let's get started. In this video we are not going to design all of that today. We are going to take it step by step. So for today we are going to see how to convert from DC to DC in the half bridge topology circuit. So for that we are going to require capacitors, these capacitors, primitive capacitors and period. Okay, aside from that, so we need two MOSFETs, switching them complementarily. That's n-channel MOSFETs. We have to switch them, so let me say generic, and we take this option, after which we make use of transformer 2. Now that transformer, we are going to take ideal transformer, one which we are just going to set the 10 ratio without taking into consideration and all of the rest. And then added to that too, once you are converting from DC to DC voltage in the half bridge topology, we start first by converting DC to AC, from AC back to DC. So to get back DC from AC, we are going to do it by bridge rectification. Though in marketable products, they make use of Schottky diodes, which are very efficient and good for this purpose. And now we need our voltage source, which we are going to set 400 volt exactly. First, we place our voltage source and we give its value 400 volt. Now we'll be converting 400 volt DC to any voltage DC of your choice. That will simply be done by setting the transformer ratio. Now we place our series capacitors. These capacitors come in place to share the voltage. That's voltage divider, 400 volt, to obtain 200 volt charge through both capacitors. So let's connect this. Let's get to connect this other side. Okay, now let's set the capacitor value. We need to set a capacitor value as high as this. Now it will depend on your system power ratings, but since we are dealing with voltage of up 100 volt, charge the capacitance of our capacitor should be that high. And for the system in which I was working on is to support current of up to 3 amperes. So let's get to input this value. Now after we've divided the voltage through the two capacitors, we place our n-channel MOSFET. Okay, now our n-channel MOSFET here comes in place to continuously switch the voltage outputted from the two capacitors, reading each and every one of them after the other. So once MOSFET 1 comes on, it conducts through capacitor 2. Once MOSFET Q2 comes on, it conducts through capacitor 1. So we will see how to get a pulse generator for that. Now, as you can see, the MOSFET are in series. Now, the output from this circuit goes as input to the bridge rectification circuit. We tap from the middle of the MOSFET, and we also come and tap it right from the middle of our capacitors and input it at the level of the transformers. Now after the transformer gets in an AC signal, AC-like signal, which will be of high frequency, 100 kHz. So mostly what we use here as transformer in physical implementation are flyback transformers. They are very characterized for such systems. Now after we've gotten a step down in AC output, you could be using this circuit to step up your voltage. After we've gotten that, we rectify it with the use of a full bridge rectifier. is how we get to connect it. Okay, from the output of the full bridge rectifier, we're going to have a lot of ripples. So to filter out those ripples, we make use of LC. We make use of LC filters. LC filters meaning we're going to need inductor. Under inductor, we are still going to take generic inductor. Then we say, okay, inductor actually is placed in series to filter out the smooth current, and we are going to place a capacitor. Hope you notice the positive side of our bridge rectifier. Capacitor is being placed in parallel. Okay, now it goes to this other terminal. Now let's reference our circuit, that is by placing our ground. We place our ground where we have negative, and we place our ground where we have negative terminals, also at the output, and generally that's it. Now we need to look for a gate drive controller that's going to be switching this MOSFET. As I said already, try subscribing to the channel so that I keep track. Here we made use of the L6384 for controlling that, but for now we are going to be using generic components into switching our MOSFET. So to do that, we come at the level of this graph. We choose pulse. Once we've taken pulse, we come up with it at the gate of our MOSFET. Now we are going to be switching this MOSFET at a very high frequency of about 100 kHz. And to switch this MOSFET on and off, we need a high gate voltage. Actually, that is about 10 to 15 volt. I'm going to put 15 volt to make sure the MOSFET is fully switched. And the start sequence here, let this start from the reference, that's a 0 point. And yeah, rise time, all of that, physical characterizing of our MOSFET. Now for the pulse width, we are going to avoid 50% while considering the dead time of our MOSFET. Basically with 50% it's still going to work, but we already tried to resolve the issue of dead time with MOSFET. At the switching frequency right now, we're going to have 100 kHz, that's 100,000 Hz, and from there we say okay. Now we set the next parameters of our pulse generator, switching voltage 15 volt. Okay, basically if we are switching at a frequency of 100 kHz, meaning it will take 10 microseconds for a full wave cycle. So this ordered pulse generator should start at 5 microseconds. At this microsecond right now, we will make sure that while the order is on, the order has to be off. So let's set to its own pulse wave at 45%. From there we say okay. Now we are going to place voltmeters, DC voltmeters. Actually see the switching characteristics of our MOSFET. This is one here. Now we are using DC voltmeter because it's going to actually be showing us the variation in DC value. If it was the case with an AC voltmeter, it's just going to take the root mean square value. Okay, once this is placed, let's also put that at the level of the transformer input. That's what has to go at the level of transformer is an AC voltmeter. You see the AC value getting into it. Now at the output, we need to get to know the output voltage DC. Everything being set, we can simulate our circuit without any issue. We have an input of 400 volt, getting to voltage divider at 2 capacitors C1 and C2. Then the switching N-channel MOSFET switch complementary to provide a high AC signal for this flyback transformer, and after which is rectified. So let's simulate and see the result. Okay, basically here you can see the rising in voltage output. Right now, let's simulate. Okay, right now here, be able to see that the two MOSFET are switching complementarily. Like I said already, the dimension, the switching of Q1 conduct through C2 and the switching of Q to conduct through C1, and here is the AC input going to the transformer, giving us an output of 100 and something. This output actually tries to is increasing, going to 200 volt, because we have an ID transformer of 10:1. So to prevent that, we set a 10 ratio that's suitable for our system. For this case, let's say 10 ratio of 7. On simulation right now, okay, that's going to give us 27.7 volt output voltage. So basically, here is the common way of designing a half-bridge topology circuit in Proteus. Hope you enjoyed the video. Hoping to see you guys in the next part of the video, where actually we are going to be programming the Atmega board to provide the gate drive control of the two MOSFET. See you guys.